Welcome back to Tech Talk Unplugged, where we dive deep into the world of technology, data, and innovation. Today, we're exploring a fascinating aspect of database management, leaderless replication, and the intricacies of quorum systems. So grab your headphones and let's get started. All right, folks, let's set the stage. Imagine you're managing a large database system. You want it to be reliable, fast, and able to handle failures without a hitch. That's where quorums come into play. A quorum is essentially a minimum number of nodes that must agree for a transaction to be considered valid. This setup allows databases to tolerate individual node failures and maintain high availability. Now here's the kicker. Databases with leaderless replication don't just stand strong against failures, they can also handle slow nodes. Instead of waiting for every single node to respond, they can return results as soon as a certain number of nodes. Let's call them W for writes and R for reads, respond. This flexibility makes them ideal for applications that need quick responses and can live with occasional stale data. However, it's not all sunshine and rainbows. While quorums are designed to help, they can still fall short in the face of network issues. Picture this. A client is trying to access a database, but due to a network interruption, it can't connect to enough nodes to form a quorum. Even though those nodes are alive and kicking, they might as well be dead to that client. This situation raises a crucial question for database designers. Should they return an error when a quorum can't be reached, or should they accept writes to nodes that are reachable, even if they're not part of the usual quorum? This brings us to the concept of a sloppy quorum. With a sloppy quorum, the system can accept writes as long as it can reach W nodes, even if those nodes aren't the designated home nodes for that data. Think of it like this. If you lock yourself out of your house, you might ask a neighbor if you can crash on their couch for a bit. That's your temporary solution. But when you get back in, your neighbor will want you to return home. When a database accepts a write to a reachable node, it must still ensure that the data gets sent back to the appropriate home nodes. This process is known as hinted handoff. It's a way to maintain data integrity while still being flexible in the face of network issues. But there's a catch. Even when W nodes are available, you can't always guarantee that you'll read the latest value for a key. That's because the most recent write might have gone to a node outside of the usual home nodes. So while a sloppy quorum ensures that data is stored somewhere, it doesn't guarantee that it's up to date. Moving on. Let's talk about how these concepts play out in real-world systems. In implementations like React, sloppy quorums are enabled by default, meaning they're ready to go right out of the box. On the other hand, systems like Cassandra and Voldemort have them turned off by default. This choice reflects different philosophies about data consistency and availability. Now, let's dive into multi-data center operations. Leaderless replication shines here as well. It's designed to handle concurrent writes, network interruptions, and latency spikes. In systems like Cassandra and Voldemort, the number of replicas includes nodes across all data centers. When a client writes data, it sends the request to all replicas, but it typically only waits for acknowledgement from a quorum of nodes in its local data center. This means that even if there are delays in cross-data center communication, the local operations remain unaffected. On the flip side, React keeps communication local to one data center. Cross-data center replication happens asynchronously in the background, similar to multi-leader replication. This design choice helps maintain data consistency while still allowing for the flexibility of leaderless replication. Now let's shift gears and talk about the challenges of concurrent writes. In a leaderless system, it's not uncommon for two clients to write to the same key at the same time. This can lead to conflicts, and if not handled correctly, nodes can become permanently inconsistent. For instance, imagine two clients, A and B, both trying to write to a key X in a 3-node data store. Node 1 might receive A's write, but miss B's due to a transient outage. Meanwhile, Node 2 could receive both writes in order, and Node 3 might receive them in the reverse order. This lack of a well-defined order can lead to confusion about what the final value of X should be. So how do we resolve these conflicts? One common approach is the last write wins (LWW) strategy. This method discards older writes in favor of the most recent one based on timestamps. However, this approach has its pitfalls. If two writes are truly concurrent, meaning neither client knew about the other's operation, then determining which write is more recent becomes problematic. In fact, relying solely on LWW can lead to lost data. If you're in a scenario where losing writes is unacceptable, LWW might not be the best choice. A safer strategy is to ensure that each key is written only once and treated as immutable. For example, using a UUID as a key can help avoid concurrent updates to the same key. Now let's touch on the concept of concurrency. How do we determine if two operations are concurrent? It boils down to whether one operation is aware of the other. If one operation builds upon another, they're not concurrent. But if both operations are unaware of each other, they are concurrent, even if they happen at different times. This concept is crucial for understanding how to manage data consistency in distributed databases. The relationship between operations, whether one happens before the other, defines their concurrency. If we can establish that one operation occurs before another, we can safely overwrite the earlier operation. But if they're concurrent, we need a strategy to resolve that conflict. So to wrap things up, leaderless replication and quorum systems offer a fascinating glimpse into the complexities of modern database management. While they provide high availability and flexibility, they also come with challenges, especially when it comes to handling concurrent writes and ensuring data consistency. As always, the right approach depends on your specific use case and tolerance for data staleness. Thanks for tuning in to this episode of Tech Talk Unplugged. If you enjoyed our discussion, don't forget to subscribe and share with your fellow tech enthusiasts. Until next time, keep exploring the world of technology.